Okay, so for this problem, number 3, we've got a tennis net which weighs 174 newtons and is 11 meters long. We're going to use a winch to exert a 3,190 Newton force of tension on the cable holding the net. We need to figure out eventually how far that net sags in the middle. And so for this problem, we're going to assume that the weight of the net acts solely on the middle of that net. And we're going to go ahead and draw in that we know that our net is 11 meters long, and then just a horizontal reference point to help us determine the angle and how far that net is sagging towards the middle. I'm going to draw in my tension on both sides of the net because the tension is given to us. They're going to be equal because it is connected. We can also see that since the weight is acting in the center of the net, the distance from the center to either side is going to be 5.5 meters, exactly half of the 11 meters. And so to use our slick rig process, we're going to draw one half of the net, or one side, one line, and I did that in green. And then we're going to connect it with the blue side of our net, which I did in blue, which is the right. And we're going to draw in our force of weight, which is the pink, and that is 174 newtons. And we're doing this just to determine what our angles are and to give us a good reference point. I'm going to draw in our horizontal reference lines and then our theta to see, and that'll be exactly how far, what degree the net has sunken in. But we need to also solve for an angle in terms of our triangle that we just created. So I'm going to represent that angle as angle capital C, which is in red there. What I drew here, this equation, is the law of cosines, and so we're going to use that to find our missing angle. This is a unique approach to using this equation because in the past we've only used this to find a missing side. But since we have all the signs, it's not going to be necessary to do that. We're going to plug in each one of the sides. I find A, B, and C based upon our triangle up there. And then just plug in all of our values. Make sure you're careful to not mistake the lowercase c, which is on the left side of that equation, represented by 3,190, for the capital C on the right side of that equation, which represents the angle inside of our triangle. We're going to go ahead and finish up this equation knowing that eventually we're going to have to move that cosine so that the capital C can be all by itself so that we can solve for it. So to do that, we're going to take the inverse cosine or arc cosine, however you prefer to say it or think about it, and put that on the other side. So we're just going to take the cosine of our left side, and make sure you're really, really careful with your parentheses. You don't want to just take the inverse cosine of the top half of our fraction. So watch those parentheses. So if you do that correctly, you should get a value around 88.4 degrees. And so we're going to take that value and look up at our top right picture. And we need to calculate what our theta is. And we know that the angle between the straight vertical and straight horizontal in that diagram is 90 degrees. So we'll take 90 degrees from our 88.4 to give us a theta of 1.6 degrees. I'm going to go ahead and pop that triangle out here because I just think it's easier to see, but it's the same triangle pictured in that right column. So our theta is 1.6. I'm going to put that in there. We're going to solve for the y, which is the brown portion up on the top, because that's how far in the net is sagging. And then I put in 5.5 meters because that's what we know to be the distance of that net from the outside to the middle. We're going to plug that in, and since we're solving for distance, we're going to get a vertical distance of 0.15 meters or 0.15 meters of a sag down for that net. So that should give us the correct answer for our problem.